Well, in Chapter 4, Section 2, we're going to start off with the following question. Consider the function f of x, where x is the height above sea level, and f of x is the percent oxygen compared to sea level. From observation, we know that at sea level, the percent of relative oxygen is 100%. At 5,000 meters, it decreases to 50%, and at 8,900 meters, it is 30%. So the first thing we want to do is write the above three data points as ordered pairs, not changing our percents to decimals, so we are going to graph the actual percent, and then we are going to plot them on this graph that we have below. All right, so our first ordered pair is actually the trickiest one. So our first ordered pair says at sea level, we have 100% of our relative oxygen. So what is the altitude at sea level? Well, it would be 0 meters, and we would have our output as 100%. Our second ordered pair says when we are at an altitude of 5,000 meters, we then decrease to 50% oxygen. And then our last ordered pair says that at 8,900 meters, the oxygen level decreases to 30%. So we're going to graph each of these pairwise and then connect the dots with those lines. So our first one is at 0, we have 100%, and then at 5,000 meters, we are at 50%. So if I connect the dots, that gives me the line through those 2 points. So my next pair that I'm going to do is 0 and 100, and 8,900 and 30%. So 8,900 is almost 9,000, and it's up at 30%. So now I connect these 2 lines, and I get something that looks like this. So the last pair is going to be 5,050 and 8,930. So I go to 5,000 and I go to 50, which is here, and 30, which is here. And if I connect these 2 lines, for these 2 points, I get a line that looks like this. So I now have 3 different graphs, right, corresponding to the pairs of points for each of these, right? Would it be possible to draw one line that contained all 3 of those points? And the answer is no, right? Because they don't lie on a straight line. So if I wanted to use a line to model the air, the percentage of relative oxygen at a height, I could ask the question, which one of these 3 lines is going to be the best model? The orange one, the red one, or the green one? All 3 of them contain 2 of the 3 data points, right? But which one's going to be the best way to determine how much oxygen is available at any altitude? Well, that's an important question, because in real life, when we encounter data, when we do science, the first part of the scientific process is to go out and gather data. And then what do? We try to come up with a hypothesis, aka a model, that is going to determine what we have. So in this case, we would have 3 things we'd want to determine, well, which one of these is the best model? Well, if you were doing the scientific process, you would then go back out into the field, gather some more data points, and then check them versus each of these to determine which one is the most accurate. It turns out that from the mathematical side, there is a way for us to try to, quote unquote, determine which line is best. And so we're going to start that process now. It's going to be something that we're going to continue next time, and that is one of the reasons we're going to be needing our graphing device next time, is we're going to be using it in order to help us determine which line is going to be the most accurate. Okay, so now we have a couple of these lines. So now, part B says, use the points from part A to find the slope of each of these three lines. And what does the slope represent? Okay, so let's go back. We're going to find the slope of each of these lines. So let's start off with the red line. So our red line contained our first two ordered pairs. So its slope is going to be m is equal to, and our two ordered pairs were 0, 100, and 5,050. So 0, 100, and 5,050. So if we were to find our slope, m is equal to 100 minus 50 all over 0 minus 5,000, which gives us negative 50 over 5,000, which is going to reduce to negative 1 over 100. All right, so our slope for the red line is negative 1 over 100. The next line that we did was our green line, and it had the point 0, 100, and 8,930. So we find the slope of our green line, so m equals 100 minus 30 all over 0 minus 8,900. And let's see, alpha y equals, to get our fraction, 100, take away 30 over 0 minus 8,900, and we get negative 7 over 890. And then lastly, we have our orange line, which used the points 5,050 and 8,930. So our slope for that line is going to be 8,900, take away 5,000, all over 30 minus 50. So 8,900, take away 5,000, all over 30, take away 50, and we get but I did that upside down. So let's type that in right. Oh my. Let's try again. Y2, so 30 minus 50 all over 8,900 minus 5,000. So now if we do that properly, we get 30 minus 50 over 8,900, take away 5,000, and we get negative 1 over 195. So just to help us out, this is, well, this one's exact actually, is equal to negative 0.01. If we go negative 7 and we divide that by 890, we get negative 0.0078, so about negative 0.0079. And for our last one, if we go 1 over 195, we get negative 0.0051. So we notice all of the slopes for the different points are different, right? We have negative 1/100th, negative about 7.81 and then 5/1000ths, approximately. All right, so we keep going now, and part C says, find the equation of each of these lines. Use each equation to find the zero of the linear function, and what does it mean? All right, so I don't think we answered the what does it mean for part B. So let's head back to that part for 1 second before we do this. So what is it that the slope represents? Well, by definition, slope is the change in y over the change in x, right? So it's the change in percent oxygen divided by the change in meters above sea level. So what does that mean? For each meter that you go up, it tells you how much of a percent of oxygen you are losing, right? So for each meter you go up, you're in the first 2 points, you're losing 1/100th of a percent of oxygen. In the second one, you're losing about 8/1000ths of a percent of oxygen, and in the orange one, you're losing about 5/1000ths of a percent of oxygen per meter. So that's what our slope represents. Part C, find the equation of each of these lines. Use each equation to find the zero of the linear function, and what does it mean? All right, so in red, that's going to be our easiest one. We have our slope, m is equal to negative 1 over 100. And this one, we actually know the y-intercept. The y-intercept is 0, 100. So that gives us the equation of the line is y equals m, which is negative 100x plus 100. All right, in green, we have our slope. This one's also pretty straightforward. Our slope is negative 7 over 890. And we're also using the y-intercept of 0, 100, right? So the equation of this line is y equals negative 7 over 890 plus 100. And lastly, we're finally to the orange. This one we're going to have to do a little more work. We have m is equal to negative 1 over 195, but we're not using the y-intercept this time. So we're using the point 5,050, and as we discovered in the previous section, if we use the other point, we're going to get the same answer. So if you want to use 8,930, by all means do so. It's not going to change anything. So this time we do y minus y1, so y minus 50 is equal to m, which is negative 195, times x minus 5,000. So we get y minus 50 is equal to negative 195x, then we distribute the negative 195 or over 195 into our fraction. So times our negative 5,000. And we get 1,000 over 39. And then we need to add 50 to that. So plus 50. And we get 2950 over 39. So y equals negative 1 over 195x plus 2950 over 39. So those are each of our three equations. So let's go ahead and put each of these into our graphing device and see what we get. So let's go with our first one is negative 1 over 100. X plus 100. Our second one is negative 7 over 890. X plus 100. And lastly, we have negative 1 over 195. X plus 2950 over 39. And we're going to graph, and it's not going to show us anything because our window is all messed up. So let's take a cue from our graph here, and we see our axes look something like this. So let's go from 0 to about 15,000 on the x, and we're going to go from 0 to 100 on the y. So we go window. We're going to make our x-min, I'm going to go negative 1,000 to give myself a little breathing room. I'm going to go out to 19,000 to make sure it fits, and then I'm going to scale in the thousands. I'm going to make my y-min 0. I'm going to make my y-max, let's give ourselves a little room here. Let's make our y-min negative 10. Let's make our y-max 110. And let's go ahead and scale this thing in tens. That's our red. This one's going to be our green. And this guy is our orange. So each of them have intercepts. And what is it that the x-intercept is going to represent this time? So when our graph crosses the x-axis, what does that represent in this picture? Well, what is the y value on the x-axis? Well, what does the y value represent? It's the percent oxygen. So when our graph intersects the x-axis, it's telling you the altitude above sea level where there is 0% oxygen. We can use our graphing calculator to find those zeros. So we go second and calculate, and we want to find our zeros. So notice in the top part of my calculator right here, it says y1. Well, y1 is my red graph, so let's find it. So am I to the left of my 0? I am. Now I move my cursor to the right, so I go below, hit enter, and then I move back and say guess. And it tells me that the 0 for the red graph is at 10,000 meters. So note, we could have also gotten this by just setting our y equal to 0 and solving. If we go 0 equals negative 100 x plus 100, if I solve this equation for x, I minus 100, I minus 100, gives me negative 100 equals negative 1 over 100x. I then multiply both sides of the equation by 100, or negative 100. So negative 100 times negative 100 is 10,000. Positive 10,000 is equal to x, which is the same number we got here, right? Because we were finding the x coordinate when y was equal to 0. That's how you find x-intercepts. We can do the same thing again on our calculator, but this time it got a little crowded at the bottom. So I'm going to go back to window this time, and I'm going to make my y-men a little bit smaller. I'm going to take it all the way down to negative 40. So that I can see on the other side a little bit better. It's not going to change the numbers, just the picture. So now I want to find the 0 of my second function. So I go second, calculate 0, but this time I don't want to do y1. So I press my down arrow, and notice that my calculator now says y2, and it shows its equation in the upper left-hand corner. So now when I go second, calculate 0, instead of moving along, second, calculate 0, I move down, I press my down arrow to go to y2. I'm still to the left of my 0, so I hit enter, and now I move to the right of my 0. Hit enter, and then I move back guess. And this time it tells me 12,714 meters approximately. And lastly, we're going to do the same thing. So second, calculate 0. Hit my down arrow twice this time to get to y3. First curve to the left, move to the right, press enter, and then back to my guess. And this time I get the 0, 14,750. So for each of them, it tells me 3 different heights. And we'll notice, depending on which model we used, there's almost 5,000 meters difference on when we would run out of oxygen, right? 10,000 meters, 12,714 meters, and 14,750 meters, right? So it once again circles back to the question, well, which one of these is the best model for our oxygen? So if we go back to our calculator and we go second table, and we want to look at it, right now our table's not very usable because our x is counting in ones, which isn't very helpful. So you'll notice that on the bottom it says, press plus for delta table. If we press our plus key, we can then change what our x's are going to change by. So if we look at our original graph, what are our x's changing by? Thousands. So that seems like it would be a good way to look at it. So we change our delta x to 1,000. And now we can see our percents oxygen and so forth when we look at them in our table. So we'll notice in this, they're very hard to read because it's giving us fractions. If we want to force our calculator to put decimals in our table, we go to y equals, and we use our arrow until we get to the right of what we have here. We press math, and we take choice number 2, and we say, please give me decimals. And we can do the same thing once again. Scroll to the end, math, choice number 2 for decimal. And lastly, we do the same thing here. We get to the end, and we go choice number 2 for decimal. So now when we go back to our table this time, we can scroll over and we get our different percentages. So notice when we compare our different models here, y1 and y2 say at an altitude of 0 meters, how much oxygen do we have? 100%. But when I look at y3, how much oxygen does it tell me we have at 0 meters? 75%, right? Oh, that's interesting, because we know that's incorrect. If we go down to 5,000 meters, we'll notice we know at 5,000 meters we have exactly 50% oxygen. Model 1 agrees, Model 2 says we have 60, and Model 3 says we have 50. So this time it's Model 2 has the error. And if we get down to around 8,900, so 9,000, Y1 says we have 10% oxygen, Y2 says we have 29%, and Y3 says we have 29%, when the actual answer is 30%. We're pretty close. So we notice each of these lines has errors in the approximation. So the philosophical question then is, well, is one of these lines the best model? And if so, how can we rank and compare which ones are better? Because our goal is to come up with accurate models. And we know that none of these are 100% accurate, so which one's the best, right? So that's going to take some definition, because we have to quantify, well, what does it mean to be the best line that approximates a data set? And how can we measure that? Because it's not a quality judgment, right? We want to have an actual scientific measure that allows us to determine which of these things is going to be the best. All right. So we are going to take a break from that and switch to our next example. So example is Anna and Emmanuel start at the same intersection. Anna walks east at a rate of 4 miles per hour, while Emmanuel walks south at a rate of 3 miles per hour. They are communicating with a two-way radio that has a range of 2 miles. How long after they start walking will they be out of radio contact? All right, so let's go ahead and draw a picture to help us get started. So they're going to start here at this intersection, and we know that Anna is going to be heading east, and she's walking at 4 miles per hour. And Emmanuel is heading south, and he's walking at 3 miles per hour. So then the distance between these two is going to be the hypotenuse of that triangle, right? So that's our distance. So the distance traveled by Anna, we know that our model is distance is equal to rate times time. I'm going to use A for Anna. Her rate is 4 times t, where t is measured in hours. For Emmanuel, we'll do the same thing. His rate is 3 times time. So then in terms of our triangle, what we're going to have is the length of each side as a function of time is going to be 4t and 3t. So if we know the side lengths of two sides, or the legs of a right triangle, what theorem can we use to help us find the distance? Well, that's going to be the Pythagorean theorem, right? So by the Pythagorean theorem, we know that the distance squared, so I'll call that d, is equal to a squared plus b squared, so 4t squared plus 3t squared. So that's going to give us 16t squared and 9t squared, which equals 25t squared. So then, just d. And then we get d is equal to the square root of 25, which is 5, and the square root of t squared is the absolute value of t, but we don't actually need that here because time will always be positive in this context. So the distance between them is 5t, right? So that says that the distance in between them is increasing at the rate of 5 miles per hour. So if they are communicating on a two-way radio that has a range of 2 miles, we want to know, well, when does the distance equal 2 miles? So we need to solve 2 is equal to 5t. We divide by 5, we divide by 5. And that gives us t is 2/5 of an hour. But most of the time we don't talk about things in fractional hours like that unless they're nice things like quarters and halves. So in the event we wanted to know what that is in minutes, we would go 2/5 times 60, which would give us 24 minutes. And either one of those would be a good answer. I'm fairly certain in the homework they're going to ask for the answer in hours, but people will look at you like you're a weirdo if you tell them I'll be there in 2/5 of an hour. So it's often good to convert things to minutes. All right, next example. There is a straight road leading from the town of Westboro to Agratown 30 miles east and 10 miles north. Partway down the road, it junctions with a second road perpendicular to the first, leading to the town of Eastboro. If the town of Eastboro is located 20 miles directly east of the town of Westboro, how far is the road junction from Westboro? So once again, a good diagram is going to help us figure out what it is we're trying to find. So if we start and label here's Westboro, W, and then we know that Agratown is 30 miles east and 10 miles north. So in terms of our picture, I'm actually going to draw a graph, and I am going to put Westboro at the origin, so it's at the point 0, 0. If that's the case, then our x-axis, the positive x-axis, is going to correspond to east, and the positive y-axis is going to correspond to north, right? Because if we look at our cardinal directions, north, south, east, and west, so then we're going to have Agratown is going to be 30 miles east and 10 miles north. So 10, 20, 30. And if we go 10 north, we're going to have our other city here. And it's going to be at the ordered pair 30, 10, right? Partway down the road, it junctions with a second road perpendicular to the first, leading to the town of Eastboro. If Eastboro is 20 miles directly east, so that's going to be here. So in terms of our diagram, we have our road that connects these two cities, and then it says partway down this road, we have something that is perpendicular to that road that leads us exactly to that point. So just to help, this is located at the point 20, 0, and what we are trying to find is this point right here, right? So this is what we want. So once again, one of the key things that we're told is that this is perpendicular, right? So that helps us figure out a couple of different things. So first of all, if we look at our line that connects Westboro and Agritown, we know Westboro is at the origin, so 0, 0, and Agritown is at 30, 10. So what is going to be the slope of this line? Well, slope is y2 minus y1, so 10 minus 0 over 30 minus 0 gives us 10 over 30, which reduces to 1/3. Well, if that's the case, what do we know about lines that are perpendicular? So since these are perpendicular, what does its slope have to be? Well, things that are perpendicular, the product of their slopes is -1, or they are negative reciprocals. So the negative reciprocal of 1/3 is going to give us the slope of -3. So we have the slope of this line is -3. So then we have something that looks like this. What we really want to do is find the coordinate of this point. Well, we know the slopes of each of these lines. So if we find the equation of this line right here that connects the towns Agritown and Westboro, we know that it has slope 1/3, and what's its y-intercept going to be? 0. So the equation of that line is y equals 1/3 x. We know our other line, the one that's perpendicular to it, contains the point 20, 0 and has slope -3. So y equals -3x plus b. So 0 is equal to -3 times 20 plus b. So -60 plus b is equal to 0. Add 60, and we get 60 is equal to b. So then the equation of that line is going to be y equals -3x plus 60. So now our goal is, well, where do those two lines meet? So we set them equal to each other, and we solve. 1 over 3x is equal to -3x plus 60. So we clear our fractions by multiplying everything by 3. And that gives us x equals -9x plus 180. We add 9x, and we add 9x, and we get 10x equals 180. Divide by 10, divide by 10. So we get x is equal to 18. Then to find the corresponding y value, we plug that in. So y is equal to 1/3 times 18, and that gives us 6. So we get that the ordered pair of the point of intersection is here at 18, 6. So we've been doing a whole bunch of stuff there. I almost forgot. What is it we're trying to find? How far is the road junction from Westboro? Well, that's going to be this right here, right? But if we know, drawing this down here, that this point is at 18,6, there's a few different ways we can get that value. The easiest one is once again the Pythagorean theorem. So our distance d is going to be d squared is equal to 18 squared plus 6 squared. So 18 squared plus 6 squared. Let's try that again. 18 squared plus 6 squared gives us 360. So then taking 360 is 36 times 10. Taking our square root then, we get the square root of 36 times 10, which is 6 square roots of 10. So the distance is 6 square roots of 10, or if we need a decimal approximation, we can just take the square root of 360. And we get that it is about 19 miles, right? All right. So in both of these problems, the key thing that really helped us out was drawing a good diagram. In both of these examples, we ended up using the Pythagorean theorem, which is a squared plus b squared equals c squared. And in this last problem, we used the fact that we know if two things are perpendicular to each other, their slopes must be negative reciprocals, right? So keeping all of those things in mind, you'll run into some stuff in the homework that is similar. All right, so lastly, so let's take a look at each of these. So let's label them as the first and the second companies. And we're going to be coming up with our cost function for each. So the first charge is an upfront fee of $50 and then 60 cents per mile. So the one thing we have to be a little careful with, 60 cents per mile is $0.6. And that's going to be our marginal cost, or the slope. That's the amount that changes as a function of distance, whereas the $50 is the fixed cost, which is going to be our y-intercept. So our equation as a function of distance is going to be 0.6x plus $50. For our second company, our marginal cost is going to be 95 cents a mile, so 0.95 times x plus the fixed cost of $10. And we were asked, for how many miles will the second company charge less than the first? So what we really want is the second company is less than the first. So we need 0.95x plus 10, and we want that to be less than 0.6x plus 50. So we minus 0.6x, we minus 0.6x, we minus 10, we minus 10, and that gives us 0.35x. Those reduce out, and that is less than 40. So then we divide by 0.35, and we divide by 0.35, giving us divided by 0.35 gives us 114.29-ish. So about 114 miles. So somewhere between the 114th and the 115th mile will the first company will then start costing less. So the first company costs more just to show up at your house, but then they charge you less per mile. So if you're moving less than 114 miles, it would be to your benefit to choose company number 2, even though they have a higher cost per mile because they have a lower fixed cost. Whereas the first company would save you money only if you were moving a distance greater than 114 miles. And at about 114, they would be approximately the same.